Last week, we have discovered the structure of how addresses are, what are the layering principles of the internet, and we finished with the IPv6 addresses that I'm recalling here. We very quickly went into the fact that with IPv6, every system always has a global address and a link local address. That's part of the difference between IPv4. The link local address means it's an address that can be used only when we don't use routers. So if A and B communicate and they think they are in the same local area network, then they can, and in fact IPv6 say they should, use their link local address. Why this is so is a long story. It makes the thing a bit complicated, but that's the way it is. So we will see such addresses. For example, if I analyze my configuration here at EPFL on this is a Macintosh. I see, no, here I don't see the link local address. We'll see it on this example here. If we analyze what this router here, so that's again a figure of what we saw with IPv4, a router that's on the backbone of EPFL that has a default route that goes towards the backbone. That's the 0. So in IPv6, we write a default route with zeros. Zeros everywhere is the double semicolon. /0 means that's the empty prefix. And then it says every packet that should go to the default route should go to this router. With IPv4, we would give the IP destination address of this router. But by definition, if two routers are neighbors of each other, that means they are on link of each other. They're in the same local area network. At least this interface and that interface are in the same local area network. So with IPv6, they should use as destination address the link local address, which is this one for this router, FE80:1. That means lots of zeros and a 1 at the end. It's atypical that the link local address is so small, so short, but it can happen. And here it's convenient to make it short. So therefore, we say the next hop for 0 is this F801. If in contrast, we go to this, this network here, which is towards the rest of the switch network, which is given with this prefix here, then 2006.26.18.10a, then which we find here, /64, so that means only this subnetwork, should go to this router, and then the next hop, since it's also on link, should be given by its link local address, which is FE80:1, which is the same as this one. Is it a bug? Is it a mistake? It's rare that the link local address is the same, but if it is configured, very often when we organize a network, we give simple addresses to the routers. We get 1, 2, 3, 4, etc., to make the debugging easier. So that is what we did here. Any default router has an address 1 here. Here it's the same link local address. Is it a bug? No, it is not, because by definition, a link local address has scope, a certain local area network. So it should be unique within a local area network. You're not supposed to send a packet to this one, for example, from here by using this destination address, because from here to there, we are not link local. We should go through a router. So it's not a bug, but it might be confusing if we're not used to it. This is why we have a look at it. So, of course, this means simply giving the destination address is not sufficient. You also should specify on which port it is, which is typically also present in the routing table. There's an interface number. And to make sure there is no ambiguity, sometimes we add some additional suffix to the address in routing table. For example, here we add, this is the Windows notation, we add %1 on Unix and Macintosh, there is a different notation. We add a scope ID, that's the way it's called on some systems, that says this is this address within this local area network that corresponds to this interface here. So it is in some sense the interface number. If we look at the IP packet format, here I did a trace route to this destination. Trace route uses, depending which version you use or which option you use, it uses UDP typically, but may use also ICMP or other things. Here it's using UDP, and I'm analyzing the packet that I've sent. So I see here it's not the packet that I've sent, it's the packet that I have received. I'm going to this www.ethz.ch, which gives this address here, 200167C, 200167C. Yes, it's the destination. So it's the packet that I'm sending to this destination. We see here all the fields that are present in the headers. We see the Ethernet header. In the Ethernet header, we see there is something called type IPv6. That means the Internet header contains an indication of what is the nature of the packet that is carried. And we see that this nature is different, whether it's IPv4 or IPv6. So it's not saying it's an IP packet and then the version number should say it's 4 or 6. It's done a bit differently. It's the here the Ethernet that says it's IPv6. We find here a testimony of the fact that IPv4 and IPv6 are really treated as two independent network protocols. They're not just one different version of each other. Then we find the IPv6 header, which contains a number of things that we will discuss. It contains the source address. That's me. That's my address. It's my address from home. So at home, I have IPv6, like you probably all have if you use ADSL modems. Destination address, which is that of the host I'm trace routing to at ETH. It is saying it's UDP. It gives the source and destination port. And here it also has the hop limit, which in IPv4 is called the TTL. Here is 7. TTL was a wrong word. TTL stands for time to live. It means a time in seconds, but in reality, it's a hop. It's a hop count. We count how many routers we have crossed here. So in IPv6, people change the terminology to align with what it really means. Good or bad idea, just make things worse to understand. But the assumption is that sooner or later, we will do only IPv6, so it's better to have a good terminology. So hop limit is 7. And then we see essentially a UDP payload of 12 bytes, which is essentially random bits that are sent, here 12 bytes, that will be sent to a destination that probably will simply dump it, because the UDP destination doesn't have a server that's expecting us to do traceroute to it, so it will simply dump it. But as we know from the story of traceroute, the error messages that will be sent on the way, here, for example, a hop limit of 7 is atypical. So most systems, except those in New Zealand, perhaps, they put a source at the source, a hop limit of 64. That's what we've seen last week. To large enough so that it reaches the destination. But here we're trying to analyze the path to the destination. So we put a hop limit of 7, and the 7th router on the path will reply with an error message that the traceroute software will analyze to display the results. What we have seen when doing that is the fields that are in the IP packet. IPv4 is given on the left, IPv6 is given on the right. IPv4 contains, like IPv6, the source and destination address. One line here represents 32 bits. We see that IPv4 source and destination address are considerably smaller than IPv6, as expected. In fact, the IPv4 header is 20 bytes. The IPv6 header is 40 bytes. If we had the TCP header, which is also typically 20 byte, we see that in order to, before sending any useful information, we already consume 60 bytes just of headers when we use IPv6. That's the price to pay for modern TCP/IP protocols. Then there's a number of other fields that we will not discuss in detail. One of them is the TTL versus hop limit, which is 8-bit, which means the TTL can be anything between 0 and 255. I said 256, it's 255, the largest number we can put here. And something which is called in IPv6 next header, and in IPv4 protocol. Very much like an Ethernet packet header contains a field that says what is contained inside the Ethernet packet is IPv4 or IPv6. Similarly, the IP header says what is contained inside the IP packet, which is typically UDP or TCP or ICMP, the Air Control Messaging Protocol. Those are the 3 typical cases, and that's why it's called protocol type, the protocol being typically TCP or UDP. But sometimes, as we will see in a few more minutes, we put packets in packets. For example, we might put an IPv4 packet inside an IPv4 packet. That's a bit weird, but you could imagine putting, for example, an IPv6 packet inside an IPv4 packet when you want to carry IPv6 packets across a part of the network that does not have IPv6 routers, for example. So this generalization means that what we have next is not necessarily TCP or UDP. That's why it's called next header in IPv6. But the meaning is exactly the same. Voila, time to do a quick recap of what we've seen. Here is a little quiz. And the room number for speak up is 24767 as written on the board here. Close the poll in a few seconds. Closing. Here the prefix length is 64. That's a simpler way of giving the subnet prefix, which can also be done by using mast. So here 64 means it contains 1, 2, 3, 4 groups of 16 bits. So it means the prefix is identified by the four first groups. A and RW are on the same LAN, so they should have the same subnet. The rules are the same for IPv4 and IPv6. RE and SW are on the same LAN, so they should have the same subnet. And the subnet should be different from here to here, and similarly there. So here the subnet is given by looking at the beginning. We see that it should be 2001.123. So the only possible answer is B, which is the majority vote. Another question? So here it might be a bit ambiguous. Here, this line here is not interested. We've solved it. So I will delete it. So we're looking at the linked local addresses of A. Whoops. Closing the poll in a few seconds. Closing. And the short majority says F, which means B and C, which is the correct answer. Here, the link local address should be unique within A and RW. Of course, this is a highly academic example where there are only two interfaces in a subnet. Typically, there are more, but that's how it is. So the only constraint is it should be different from this one. So A is not possible. B and C are possible. Here I have an example where I choose the link local address, which you can do by manipulating your if config term. But typically, this is done automatically by your system. That's the goal of the link local addresses, is in fact, unless you are designing a network like you sometimes are, where you want, for example, the routers to have addresses that are easy to understand. Otherwise, if you particularly at a host on your smartphone or your computer, when you boot, you will obtain an address that's automatically computed, typically by hashing your MAC address. So that it will have something that is unique and does not have any meaning, like we can see if we look at our systems here. Now, a more philosophical question. I have interconnected 4 systems with a box, which is programmable. Many boxes are programmable. For example, if you have what is called your modem, if you are a customer of Swisscom, Sunrise, Salt, you will receive a box that terminates the line from the operator, and that has a number of Ethernet ports to which you can connect your own devices. And then by software, you can configure it as a router or a bridge between your different elements that you use here. So here, I'm assuming I am in this situation. I have 4 systems here. I'm not even connected to Swisscom or anything. I'm just interconnecting my printers and my computers and perhaps a disk here. And originally, I was running IPv4. Then I was convinced after this course to move to IPv6. So I changed IPv6, which is easy here. It's just enabling the software here. In fact, if you have a fairly recent software, if you buy a printer today, it will come by default with its IPv6 interface enabled, not the IPv4, because that's expected to be the default here. So I move everything to IPv6. That's easy in the hosts and in the systems. What should I do in the box here? Should I reconfigure it? That's the question I'm asking. So if it was originally an Ethernet switch, I want to keep it as an Ethernet switch, which means as a bridge. Should I change anything when I move from IPv4 to IPv6? And same question if it was a router. I close the poll in a few seconds. The majority says A, which is the correct answer. Because if we have a router, then we have a numbering plan. The router should know what is the subnet on each of its ports. If it had some information for IPv4 only before, when you move to IPv6, well, you need to put this information in place. So you will need to do something. You will need to at least type in the numbering plan. You have to decide which prefix you want. What's the prefix length? 64, 96. 92. You can do anything with IPv6. You have a huge freedom because the address is so large, but you have to decide something. So if it's a router has to do with IP addresses. V4 or V6, they represent the choices you made about how you build your network, how you organize subnets. So you should renumber it. So with IP, there is a configuration word. Now, if it's an Ethernet switch, which means if it's a bridge, we've seen that the bridge reacts only to MAC addresses. It doesn't even look at IP addresses. So since it looks only at MAC addresses, as long as plus it does it, as we've learned, completely automatically. So whether you change the software or you enable IPv4 or IPv6 doesn't change, in fact, anything here. If you don't change the physical hardware that you have here, it will not even see, it will not even notice that you had done a change in the host. In fact, this slide explains why we continue to have both the MAC and the IP layer. It is because in an example like this, we see that interconnecting things at the MAC layer is considerably simpler. Introducing IPv4 or IPv6 doesn't change all the MAC layer infrastructure that you have, whereas for IPv6 and IPv4, there is considerable pain and visibility of IP everywhere. Voilà. So that's the end of the first part of the network and MAC layer, which is what I would call the correct architecture. This is how things should be. Now, if you did at home, some of you, in fact, posted on Moodle one question about what addresses I see, and the answer by Ludovic, well, the address that is seen from outside is perhaps not exactly the address you see from inside, because at home, you will be probably using something called a NAT. A NAT is something that is a violation of the architecture. It is not following all the principles we've done before. And it's a pragmatic answer that was deployed to address essentially the problem of not having enough IPv4 addresses. Not only we don't have enough IPv4 addresses, we can't sell new addresses anymore, but worse than that, when IPv4 was done, the assumption would be that people have zero. Most people would not be connected to the internet. It was an academic thing or research or industrial environment type of facility. But you were not expected to have many hosts. Now, today at home, you probably, if you are several people living in the same colloq, you have probably a number of computers. You also have smartphones. You also have visitors. You have friends who come and visit you. They connect to your Wi-Fi. So they also need their own IP addresses. So if you look into the ifconfig or the tables of your ADSL modem at home, if you find the password to log into it, you will see the list of all the IP addresses that have been allocated by DHCP to you or visitors. And if you have not flushed it, you will be surprised to see probably tens or even 100 or 200 addresses, because perhaps you forgot, but 2 years ago you changed your smartphone, you have a new one, you have a new IP address, and so you have a large number of IP addresses. But for IPv4, from Sunrise or Swisscom, you will obtain only one, because IPv4 addresses are rare, expensive. They don't have that many. They will give at most one to you. So how can you have a problem? The principle of IP is one IP address per interface. So when you have a modern infrastructure like we have today, providers should give to you not one address, but a prefix, so that you can organize your own subnetwork. This is what they do with IPv6. When you receive IPv6 connectivity from your provider, they don't give you just one address, they give you an entire prefix of 64 or 80 or 92. They give you a prefix that will allow you to build your own network, which is the normal way we discuss the internet layer is organized. But with IPv4, it doesn't work. So we need to find a hack. What is the hack? Well, the hack is, first, we use private addresses to you at home. So if you look at your IP addresses at home, you will see addresses that are private. By doing this, I can number all the systems I have, and I can send from my smartphone to my printer. They all have IP addresses. But of course, it's a problem. How can I communicate with the rest of the world if I have only IP addresses? And my interest at home is certainly not just to print my homeworks on my printer, but certainly to go on the internet. So I want to be able to go to the public internet. So how do you do this? Well, we will use a box that is called a NAT, that allows us to use private addresses to connect to the public internet, and also to share one IP address between several machines. So my NAT has this address that I received from Swisscom, for example. That's my address I have from home, and that's the address of my NAT box. And then my NAT will, at home I have an entire network, like we've seen in all the exercises we do, but we use private addresses here. This is used also in another environment called virtual networking. is what is done very often in practically all server rooms when you go to Google or Swisscom or Facebook or whatever, whatever server farms they have, they typically put logical servers inside physical servers using virtualization. And in some of the labs, those who do the advanced lab, they use also, and in some of the advanced part of this lab, you'll have the opportunity to use this. So we use what is called virtualization software that allows you to have your machine, your Macintosh or Windows software operating system. And then you have a software called there's VMware, VirtualBox, etc., that allows you to have other operating systems inside your machine. It's very often used, for example, if you work on, if you have some software that works only on Windows, like in electrical engineering, you have sometimes software that works only on Windows, so you will want to have Windows even though your computer is a Macintosh or vice versa. So you might do this, and very often this is to put Linux systems that have no dependency. You can put whatever version of Linux you want here, which is typically a stripped down version that has only the things needed for a given application. That's what we do in the lab, in the advanced parts of the lab, for example, to run one version of Linux. And also you can have many, many different ones. So we can start playing in the lab as if we had several machines to do a true network. That's not the goal in server environments. In server environments, server farms, the goal is really to separate the software dependencies. Yes? Oops, sorry. Exactly. So you have the question. So here you do all this in software, and you use also private addresses, and you do exactly the same thing as you do at home. You put an app. No, it's not a physical box. It's a software app. But if you think about it, that's exactly the same situation. You have a physical system that has a physical address here. Now it needs to share this physical address between a number of devices that here are purely software, or here are physical independent boxes here. So how can we do this? How can we do the two things, sharing the same address between several systems and then using private addresses? Well, the solution is translation. NAT stands for Network Address Translation. So the NAT will translate the address. This is from the private to the public. So let's see here. When A sends a packet to S, so sends a UDP packet in that case, perhaps for whatever reason, A sends a UDP packet to S, so it sends from, if we look at the packet sent to A, it sends to the address 1234 of S. Then the routes into your local area network, you have routing table and everything as usual. It will lead to the default router, which must be the NAT here. The NAT receives this packet. Now it has a packet to send to this address. Now the NAT doesn't act as a router. It acts as a special device called a NAT, where it will see, oh, the destination address is outside. A NAT has an inside part and an outside part. Internal network, external network. Also, if you look at the documentation, it's very often called the LAN port of the NAT and the WAN. WAN stands for Wide Area Network. It's not necessarily very far away from you, but it means the external here. So the NAT says I have a packet to send to an address that's external to me. So I have to translate the source address. So if we look at the packet as we look at it outside of the NAT, it will be sent from the source address, which is the IP address of the NAT, which is the only one that's usable. That's the address that my service provider has given to me. And the destination is the same, and it is also a UDP packet with UDP source and UDP destination. And we see that while doing this, it may change the UDP source port. So it changes the IP source address and also the UDP source port. Changing the IP source address, we understand why it does this, because that's the only possible way to have a response coming back to me, because that's for the rest of the world, that's the only address that's visible. Why do we want to change the IP source address? Well, because we need to do two things. We need to replace the private address by a public one, but we also need to share a single address between more than one system. So, so what the NAT does, it pretends that A is the NAT for the rest of the world. So it impersonates A in this address here. But when a packet will come back, how can the NATs know whether the packet is for A, for B, or for the NAT itself? The NAT very seldom receives packet, but once in a while, Swisscom might send some software update to your NAT. You don't even know. So it might send software to the NAT itself. So how does it know it's a packet for the NAT or for A or for B? Well, there's a pigeonhole problem. If I have 32 bits, I cannot, if the address size is fixed, I cannot have more. There is no way to differentiate between A and B in the address field. So I need to steal, I need to have some space somewhere. And this is done by stealing from the port number. How does it work? When A and B sends packet, assume that it's a pure coincidence, but it may happen. And on the millions of packets that are exchanged every day, that will certainly happen once in a while. Assume that they are both accessing the same server at about the same time, and the operating system have given them the same source UDP number. It's unlikely that it happens, but it's also not impossible. And if we repeat the thing many, many times, once in a while it will happen. Assume it happens. Then the NAT, when it will send those packets from A and B to S, it will change the source address to itself, to the NAT source address. And then there's a problem. If it doesn't change the UDP source number, then the two packets will have exactly the same header. So they are confused now as if they would be coming from the NAT, which of course would be stupid. It doesn't work. They're not coming from the NAT. One is coming from A, one is coming from B. So the trick is to change the UDP source number and remember it. So the NAT has a table that says here, when I sent a packet from this is A, which had this port number, I translated into that. Well, that's me. That's completely obvious. But here is the port number that I chose, that me, NAT, I chose for this packet. And I remember it and I put it in a table. So this manipulation of the port number is, of course, in principle, not allowed. I mean, this is a networking box. We've seen that the transport layer is end-to-end. The transport layer is the business of A and S only. But that's a pragmatic thing. This is why I say it violates the architecture. This is how things are in the real world here. So what happens in the reverse direction? So A and B have sent packets to S. S replies. S is, for example, perhaps a DNS server or whatever they were doing traceroute. S sees two packets coming from those two addresses, which are twice the same, with different port numbers. So from S, it is as if the NAT was talking to S, as if there was a computer in the NAT with two different processes, perhaps two users that are logged in remotely to the computer and are both sending packets to S. For S, it's impossible to know whether there is A and B or whether it is simply all coming from the NAT. So it will reply to both, to those addresses and those port numbers. When the NAT receives the packet, for every packet it receives, it must go through its NAT table and find an exact match. As opposed to a router that looks for the longest prefix match, here the NAT will look for an exact match. A bit like a bridge, but it's even worse than for a bridge because it's an exact match for all the combinations of destination addresses and port numbers. So if it's potentially many entries. So NATs, of course, work at the small scale. It's not scalable, even though there are bigger NATs with very expensive technologies. But in principle, it's not scalable because we need to do the exact match. So the NAT will look in its table for what are all the internal port numbers. So it's for me here, my address. So I look for an exact match in the right part of the table. I find two. But in general, as you can imagine, if you have a number of machines that are working, there are all the flows that are activated here. Question?
Yes. Sorry, for S to communicate with A or B before A or B actually try to communicate with S.
We will talk about it in a second. It doesn't work. It doesn't work. Yes?
Isn't it using only just one IP address?
Isn't it using the wrong?
Is net using just one IP address?
a typical NAT like you and I have at home, yes, you have one IP address that's given to us by Swisscom, and you have only one. So yes, there is one. Of course, you can imagine to apply the same principle. It's called, and it exists, it's called a carrier-grade NAT. For example, if you do traceroute inside EPFL, you will see that there are private addresses that are used inside the internal network of EPFL. So, and then those IP addresses are translated to public addresses by using also a NAT that in this case may have a block of addresses, not just one. So if you have an entire private network to which you have 10,000 private addresses that communicates to the public internet over a block of perhaps 256 addresses, you do the same trick, but then you will map 10,000 private addresses to 256 public addresses. That's called a carrier-grade NAT. The example I'm giving, which is a home NAT, has only one single address. So here it will find exactly one match, and it will simply translate, and the translation means the packets will follow through the local network, which is a local area network, or also has routers inside, will eventually join A and B with the correct addresses. So for A and B, things are business as usual. And for S, it's also as if everything would be in NAT. There's only the NAT that knows that the NAT trick was done here. If you look at the commercial technology, or if you ask ChatGPT, the NAT will be called a router. But if we want to have a clean terminology, it's not a router. A router is something that performs the intermediate layer function of the IP layer. And as we have seen in the many exercises we did last week, a router does not change the IP addresses. Just like the post office doesn't change the source address and the destination address. Right? It changes the MAC addresses because it has to go from one LAN to the other, but it doesn't change the IP addresses. A NAT does. It's often called a router because people don't really know those things, but it's not a router. Now, to answer your question, what happens if S speaks first, right? So if S sends a packet to A for the first time, then it doesn't work. Typically A speaks to S first, so because communication is typically initiated from inside, because you are seldom having a server at home, a web server or a mail server that's at home behind your NAT. That's rare. We'll see it's possible, but that's rare. It was frequent 20, 30 years ago. Now it's quasi impossible to do. First, because most servers now are it's much cheaper to rent a slice in a data center somewhere that will give to you a virtual machine for a few tens of francs per month instead of buying your whole machine. So from an energy viewpoint, power consumption, price of hardware, it's cheaper. And second, it's a catastrophe from a security viewpoint. If you have your own server, it will be bombarded by probably hundreds of thousands of illegal messages. So you need also a security software to do intrusion detection, filtering, anomaly detection, etc. So it's possible, but very, very rare, in fact, which is why the NATs work most of the time. So because when A speaks to S, when you go to a server, as we have seen last week, the definition of a server is that it's the side that is waiting for communication to come, which means the initiation is always from the client side, which is consistent with the operation of NAT. So when the NAT sees the packets from the first time, it creates on the fly an extra line here. So this is a dynamic table that's created on the fly by a NAT here. I'll show it here. Now, if you still want to have a server behind your NAT, for example, a web server that would be on a port, for example, this port, not typical, but it's possible for a web server, then it's not possible by the standard operation of NAT, but you can enforce it by manual configuration. If you find the password of your ADSL modem, which you can go into it, and this is called port forwarding. You can write a table here manually instead of having do it on the fly. You can decide that this IP address, this port number should be mapped to the address here. You have no choice, it must be the IP address of the NAT. And here you have to choose a port number. Here I chose the same here. That means the rest of the world will think that this server is at this address under this port number here. But this, you have to do it manually. You have to choose the numbers. And if you change the machine A or the IP address of the machine A in your local area network, of course, it will not work anymore. That's the price to pay of NATs. That's also the difficulty for what is called peer-to-peer software, like some voice over IP software of Skype, for example. If now it's peer-to-peer, if A is talking to another thing that's not a server, but something like A, then there is a difficulty here. So peer-to-peer software, usually the very first peer-to-peer software, like NetMeeting of Microsoft, required you to do this. So it was only for the happy few who were able to understand this and find a way to do it. Now, software that is truly peer-to-peer needs to find a solution to this. The solution is typically to have yet a third system that will to which you will first connect. So even though Skype is might be peer-to-peer in the sense my phone conversation from A to B might go directly from A to B, in order to call B, I will first go to a server, and the server will call the other guy who will need to reply to me, and the address of your Skype servers are pre-configured in your Skype software. So there will be still a server here that will allow you to start the communication through the NAT here. Incidentally, this, which is the result of layers of hacking, I mean, first we use IP addresses that are private. Second, we reuse the same address several times. Then when you violate the architecture once, you're forced to violate another time. It's like when you cheat somewhere, you're forced to add additional cheating to make the thing consistent. And I don't advise cheating because it's very hard to make it consistent, but it's not ethical. But here, once we warp the architecture at one place, we need to warp it at several places. But there is a good side effect, which is in fact why people are now very happy with NATs, and NATs exist everywhere. This brings a level of protection because, as I mentioned, there is a security problem with servers. There's a lot of malware out there on the public internet that is constantly trying to infect all server ports that are open. So if you open a server, FTP or SSH or HTTP server, a server or a mail server, even worse, then there will be lots of malware that is trying to send you bogus mail to your server and trying to send, if your server is not correctly patched, doesn't have the most recent software, it will use known weaknesses of the software that you use to try to infect your system and gain control of your system here. So if you run a server, you have to be aware of that, patch it all the time, as I said, have some intrusion detection software and lots of things like this. But if you just have one server with one IP address and one port, which is performing one piece of software, then you limit this attack surface to this server and this software that you must always patch and monitor. And you know that if on a machine like B, for example, by poor configuration, that seldom happens on Macintoshes and Windows systems, but on Linux, it's up to you to do your own configuration. Plus, you might have old configurations with ports that are open, for example, here. If a port is open, for example, because you try to do something in the lab of this or another course, and then you have an error message, and then the answer, you look up on the internet how to solve this error message, then the answer is disable the firewall. So the firewall is software in your operating system, in your A or B, that is try to prevent a number of communication flows from happening, typically from servers, for example. If it will make it impossible to host a server on your machine here, unless you explicitly ask for it. For example, when you install some software, it will require some changes to the firewall here. But if you have removed or disabled the firewall and forgot to re-enable it because the exercise is over, you might have a machine B that has a number of ports open, and that will, of course, receive a lot of attacks from the world. Except that now the NAT will make this impossible, because unless B is actively engaged in a communication with someone else, the packet will be dropped at the NAT because there is no traffic here. So it's a pain in the sense that opening a port requires, opening a server requires a configuration, but it's also a protection. It makes sure that only the server ports that are actively opened by you are available on the internet. Now, if we have IPv6, with IPv6, in principle, we don't need an NAT. In fact, the people who do the IP architecture, which is the IETF, Internet Engineering Task Force, have always been resistant to NATs. So for a long period of time, they were against NATs. They've tried, many people there have tried very hard to prevent NATs from happening, because NATs were a solution to the shortage of IPv4 addresses that could easily be fixed with IPv6. So instead of deploying NATs, it would be better to deploy IPv6. That's the official story of the internet since 97, for 26 years. As we have seen, it has not been very successful. NATs are very successful, and IPv6 is not so much deployed, but it starts being deployed. And now if you have IPv6 at home, which in Switzerland you typically have, you have both IPv4 and IPv6, which is a luxury. That means we are never bothered by the incompatibility because we have both. But we're, in the long term, probably would have only IPv6. If I have IPv6, then my ADSL modem is truly a home router. So because my provider will give me an entire prefix, for example, here of size 60, and if I have a prefix of size 60 here, I can have everything that's after that, I can use it for me, which means I can put a subnet mask of size 64, and I have 4 bits to identify my subnet mask. Or I do subnet mask of size 96, and have much more many bits, so I can have a huge network at home. Probably Swisscom would not be so happy, but in terms of, but that's possible here. So with IPv6, since we receive an entire prefix here, the home router is now truly a router. It's not a NAT. And there's no reason to have a NAT. That's the standard operation. So if you are curious and go at home to see how your ADSL modems, that's probably what you will see. You will see that your IPv6 addresses at home are truly publicly available IPv6 addresses here. So the purists of the IETF are happy. They say, now we've reached the clean way the architecture should be done. But then come the security people and say, that has a number of drawbacks. The first drawback is now if you have a server port that's open on B by accident, it is no longer protected, right? First thing. Second thing, your IPv6 address becomes a global address that's visible to the entire internet. In fact, before, the only thing that people would see was your modem interface. So they know you're in Switzerland, you're a customer of Sunrise or Swisscom. That's all they know. Now they know exactly, they can track you more finely by your IP address here. So this is solved by two solutions. First, the IPv6 addresses are probably not like the one I said, a 1 and a 2. You can do that. You can force your system to have such addresses. But if you don't force your system to have this, your operating system will compute what is called random addresses. It will compute a random address for A and B, and will change it every few hours. So that your addresses will change. And if you contact a server every day, then every day you will appear with a different address. Now they will know you come from this home router. Your prefix will be the same, but they will not know whether it's the same address or not. And second, most home routers that I know implement what is called port filtering. So in principle, the job of a router is to look at IP destination address and send the packet where it should be sent, following the routing table. But in addition, routers today do a number of things for security, which are called filtering. They do what I said, look at the table to know where to send the packet. But in addition, they verify a number of things to see whether this packet should be killed. And in fact, many routers kill many packets. Perhaps because that's an enterprise router or a Swisscom router, and then there is intrusion detection and anomaly detection software that is trying to detect denial of service attacks and might kill or slow down some traffic when there is a symptom that does it. And here there's a very simple filtering rule, which is to say, the home router does what the NAT was doing before, which is observe whether there has been some activity from internal to external to this port number and to this address. And if not, then any activity that comes in the reverse direction would not be allowed. So if there's a packet that comes to port B, for example, to machine B, to this address, with a UDP port so-and-so, if the router has not seen before a packet in the reverse direction with source port this, it will kill it. This is to protect from attacks against port servers. So if you think about it, the home router, which is not a NAT, is in fact simulating what a NAT would do while not being a NAT in terms of just for protection. Which means if you set up a TCP server on this port on IPv6, you will still have the problem that it will not work by default. You need to go into your home router and open this port from the internet to this system here. So this is the story for IPv6. So you see there is no NAT, but there are still some port filtering functions which require the same amount of work as a NAT was doing before. IPv6 NATs tend to exist still. They're much less widespread because the reason to have them is no longer valid, except in virtualized environments. When you are in this environment here, if you use IPv6 address here, you will have only one physical IPv6 address, not a prefix, because that's only one physical machine. So we will use here an IPv6 NAT inside virtualized environment here, which work exactly the same way as IPv4 NATs, but are much less widespread and therefore much less well-known. So, voila, a small number of questions before a break. Here are NAT questions. We observe a packet sent from B to A, and A is behind a NAT, and we have the internet public here. That means the external side of the NAT is the right side. What is the IP destination address that we will see at 2 here? I close in a few seconds. Yes?
When are we using the IPv6? Are the people from the outside can track where we are? I didn't understand.
So if you connect to a server, the server will see your IP source address. With IPv6, it will truly see your true IPv6 address. This address is made of a prefix that has been, so you can look up in public tables. This prefix has been allocated to Swisscom. So they will know you're in Switzerland, and perhaps the prices of the thing you want to buy will be a bit more expensive. But they will not know exactly your address because your machine will change address every so-and-so, every few hours. So when you connect to the server again, if you disable cookies, then the server will have the only information about you will be your IP source address. Will not you, it's you again. But most of the time you say yes to cookies, so they will know it anyhow. Okay, so about this one, what is the IP destination address? We will see. I close the poll. And the majority says B, which is the correct answer. So the IP address will be that of the NAT. It's the only possible. So B has the impression you are the NAT, in fact. Now A replies. And at point 2, what is the IP? A sends IP packets to B here. I think I was meaning point 1 here. It's not point 2, it's point 1 here. So we observe at point 1 here, the reply from A to B, what is the IP destination address that we see? close the poll in a few seconds. Closing. And the answer is C, of course. That's the address of B. So we see that even though A has private addresses, it's able to send data to public addresses. Okay. Now, same question, but we're with IPv6. I'll close the poll in a few seconds. Closing. The correct answer is D, which is the correct one here. So the home router with IPv6 is a regular router. So the IP destination address is the address of A. There's still a question. A has two addresses. Which one should it be? Well, this one is a link local address. So it could be used by anybody sitting here, but certainly not by B, which is not in the same LAN. So B cannot use this link local address. It should send this one here. How does B know which address to send? Well, it's in the source address received from A, which is this address here. So there is software, operating system software rules that says that when you send to an IP destination, if it is on link with you, which you know by looking at your IP routing table, you should use as source address your link local address. So that's the operating system here that would do. So if there would be a web server in the same local area network, it would receive it with this source address. But being outside here is not possible. So that is the answer. Voila, that's all for this part on the NATs. We do a break and we resume in 10 minutes at 10:24. We'll say a few words about the physical layer. So as we see, we're going in a random order of the layers, but that's perhaps the most efficient way to do. So the physical layer in the stack of layering is the bottom layer. That's the one that maps blocks of bits received from the MAC layer into a physical signal, which is typically electromagnetic signal. The bit rate is the number of bits that can be transmitted per second. Very often computer scientists or computer people call it the bandwidth, but communication theorists don't like it. The bandwidth is a physical quantity that says what is the width in when we do a Fourier transform of the physical system. So we're talking in the spectrum. The bandwidth is in hertz. The bit rate is in bits per second. But there is a relation between the two, which is in the simplest case is given by this formula. That's an example of a formula of information theory that says that if I have a channel, for example, a cable or a wireless channel that has a bandwidth B, so for wireless, it's easy to understand. That's the bandwidth on which this channel is defined of, for example, 2 megahertz here. If I have a signal-to-noise ratio, which is the ratio of the received power to the noise, and if the noise is not impulsive, but just Gaussian noise, then the capacity of such a channel is given by this formula here. What does the capacity mean? It means if you're smart enough, you will be able to make a coding system, a modulation and an implementation that will be arbitrarily close to that. The capacity is an upper bound on what can be achieved. It cannot be achieved, but you can go arbitrarily close to it. For example, those are numbers for an ADSL line. If you're not very, very close to the, if you have long cables, for example, you might have a signal-to-noise ratio of 50 dB, and over 2 megahertz, applying this formula says to you, the capacity is 33.2 megabit per second. And you probably can buy systems that would do 33 megabit per second. So for most cable systems today, we know how to make technologies that come close to the capacity here. You can test the capacity of your line by going, for example, to CN Labs speed tests that will load your line to find exactly the maximum amount that can be downloaded or uploaded here. Of course, we see it's proportional here. The capacity is proportional to the bandwidth, so that's why very often we confuse one and the other. If you double the bandwidth, you double the capacity for a given physical set of constraints. This is why there is this confusion, but it's better to say bandwidth. And the bandwidth, the bit rate. And when the Ethernet started, over long distance, we had kilobits per second. In the local area, we had megabits per second. But today, we reach over long distances terabits per second. So the capacity is, in fact, seems to have no limit today. It's just a monetary issue. If we invest more money, we put more optical fibers in a given bundle. If you multiply by 10 the number of fibers, you multiply by 10 the total capacity. So there's no limit practically to the capacity of the internet here. But there are limits to things like times. And it's important to make the difference, at least for some of the issues that we have, between propagation and transmission. If we do the ping command, we see the round trip time. That's the time, so you've probably tested that by now. We ping a system, we obtain the round trip time, which is the two-way delay, including everything, including the processing time by the software that runs ping on your machine and on the destination, plus all the queuing time in all the routers and bridges on the path, plus all the propagation and transmission time. What is propagation and transmission time? Here I'm showing a space and time diagram. Space is vertical dimension, and time is the horizontal dimension. I'm showing here a simplified view of what happened on an Ethernet cable at 10 megabits per second when we send bits. The bits are sent with waveforms that are here when the waveform is going down, it's a 0. When it's going up, it's a 1. This is how old-style Ethernet would send zeros and ones over a channel here. When this signal is sent over the channel, it propagates at the speed of light, which of course on a short cable seems to be instantaneous, but on a long cable is perhaps less instantaneous. So the time it takes for the beginning of the first bit to move to the beginning of the first bit on the other end, this is called the propagation time. In the air, we know the value, it's 300,000 kilometers per second. That's 10 to the power 8 in vacuum or in the air. In cables, it's a bit less. In optical cables, it's 2/3 of that. In copper, it's 75% of this, which means that to go around the Earth, according to the shortest path, it's around 200 milliseconds. That's the shortest you can do. You have not sent any bit of information. It's just when the beginning of the first bit is reaching the other end here. The transmission time is the time it takes to modulate all the bits into the channel. The transmission time is given by the technology. The propagation time is given by the speed of light until there is a revolution somewhere in the universe. It will not change ever, but the technology changes the transmission time. It's inversely proportional to the bits per second of the channel. At 10 megabits per second, we are 1,000 times, takes 1,000 times longer than at 10 gigabit per second. So that's the propagation time. And then the time it takes to send a block of bits is the sum of the two, is the time from this to that, which is the sum of the transmission time minus the propagation time. Of course, the ping command doesn't make the difference between the two, but we can analyze, for example, in different settings, what are the differences. For example, in a data center setting where the distances are very short, where the bit rates are huge, then we see that the propagation time is in fact larger than the transmission time. Propagation time is in some sense the nuisance. It's a problem. Propagation time means in distributed system, if I want to do something on a remote system, that's the incompressible time it takes to me. For example, if I want to stop a process that's running somewhere else, I press stop, then the stop will reach only after the propagation time here. So that's the propagation time is a true problem with a distributed system. This is what makes distributed algorithms complicated, and this is why once in a while you have to restart them because they are stuck with the propagation time. we see that the data center, if I want to transmit 8,000 bits, for example, is limited more than propagation time. On an ADSL modem that has 10 or tens of megabits per second, with distances that may be orders of kilometers, we see that's the other way around. On the internet, if we go very far away to the other end of the world, then we see that we're again dominated by propagation, except if we're at very low bit rate. For example, if you're using Starlink to communicate, then with a relatively small, no, here it would not be Starlink, the propagation time that's small over a relatively short distance. That's how things are. So we see, depending on one or the other, depending on the case, one or the other dominates. The propagation time is always more of a problem because that's the incompressible time that we cannot move. And when we do things like error correction, if I send a block of packets to the other side of the world and there's an error and I want to correct it, the time it takes me to detect the error is dictated by this propagation time. So I need to have protocols that are robust to this. As we said, ping measures the sum of the two. Here I did two ping to two New Zealand sites. One is the University of Canterbury. The other one is the New Zealand Herald, which is the Times, if you want, of New Zealand. And here are the round-trip times that I obtained with ping. Is there any observation you can make? Yes? The second is 4 milliseconds. The first is 300 milliseconds here. Exactly. The second one is definitely not in New Zealand because we know the absolute New Zealand is really almost exactly at the other end of the world. So there's a 200 millisecond round trip time of just propagation, plus transmission, plus all the processing times. So we can never not be below 200 milliseconds. So this is not in New Zealand, but that's a New Zealand site. Right? How can you interpret this? Yes? They have servers closer to where we are, exactly. They have what is called content caching. So this content is certainly originated in Wellington, New Zealand, but is pushed into local servers all around the world so that we can reach it here. Why do we do that? Why do they not do that? Well, it costs something to have a server to push it. So why do we want to push content? Well, because the performance is better, in particular because of TCP, as we will discuss next, where the performance of TCP is less good when we are very far away. So most content distribution systems will try to push content close to the users. Also, if you expect to have a huge number of users to receive your content, you need anyhow to have a huge set of servers. If it's more efficient to have the servers distributed in the world, given that it's easy to do now because there are has become a commodity, than to have all of them in New Zealand or in Switzerland. It has a number of advantages, but the primary reason is being closer in terms of route trip time makes TCP works better. And that gives my transition to TCP and the transport layer. By necessity, we said a few words about the transport layer already at the beginning. Perhaps now you understand why. This is because port numbers are visible everywhere, in particular in the NATs. So in order to decrypt what we see when we do a trace route or a packet trace analysis, we need to look at port numbers. Remember that there are two ways of organizing the transport layer, UDP and TCP. UDP offers a basic service. TCP adds packet loss recovery, as we will discuss in a second. So let's discuss UDP first. The goal of the transport layer is to offer a service software interface to the application layer. This is done, for example, by this. If I am a client, UDP, that is sending to a server, so this server is simply receiving a packet from the client and displaying it on the screen. So that's perhaps the simplest client-server program that you may want to do. Here is the code of this. So as you can see in Python, it's not very long, so you can verbatim copy it and run it. So the client sends a string of messages to a destination that's given to this port number. The destination is a server that runs on this port number and displays what it receives and also displays from whom it receives it. So here I'm running the server and I've seen it has received from me on this port. This is the source port number, the source IP address, and here is the message that has been sent by this program, and here is the message that has been received by that one. It's a bilingual program, as you can see. Here you notice that the IP source address is the loopback address. That means I did all the clients and the server on my machine. So the destination IP address that I gave is the loopback address, which is the standard way of debugging a program. The sockets require a number of things to be done. On the server side and on the client side, you start a socket. So a socket is an entity which essentially contains a buffer that will be used to store temporarily the messages that are being sent or received, but are not yet fully processed. For example, when you send, it takes time for the operating system to put the IP header, deliver them to the Ethernet adapter, etc. So all these things takes time. So the messages you've written must be stored somewhere, so it's in a buffer. So essentially, the socket is a buffer, and you need to create it. You need to ask the operating system to allocate some space for you. So that's what you do on the server and the client side. So you create a socket in Unix file systems, and this has been copied to all systems. Writing or reading from a socket is similar to writing into or from a file. So when you write into a file, you open a file descriptor and then you say read or write. So here it's similar, except it's not called writing or reading. It's called send to or receive from. So the client creates a socket and then sends a message by using the primitive, which in Python is called send to. Send means send a message, and to, it has the indication that it contains two arguments. One is the message we're sending, a string of bytes in this example, and second, to whom we're sending it. How do we identify the destination? By the combination of IP address and destination port number. So if I look at the code of this program, here it has declared a constant called this port number. And when we say we send to this destination IP address, which in my case is just me, but in the normal case, you need to put the IP address of the server and the port number, so the destination port number. So the send to contains the message I'm sending and the port number here. And that's all that a client does. Of course, hopefully the client might receive replies from the server, but in this simple example, it does not here. The server does the same thing, except the server needs to do what is called bind. Bind means specify exactly the IP address that we use locally with this piece of software. The client has received a port number from the operating system, but the client doesn't care what the value of the port number is. We will see it in the example. We see that this client has received this port number 57747. That program has received the port number 65261. That's a port number that is necessary for UDP to work, but has no meaning. The next time we do it again, we will have a different one. In contrast, the server needs to be on a well-known port number. Otherwise, it won't work. Remember, a server is the entity that is operating and waiting for things to happen. So it must be easily identifiable. We must know the port number of the server. So the server here does a bind. It means I am asking to be associated with this port number here. We can, if we look at all details, we can decide the port number, but also the IP address. We might want, for example, this socket to be identified, associated not with this IP address, but another one, because we have seen that machines have multiple IP addresses. For example, this one has at least two, the local host address and the address that it has for any kind of IP addresses it may have. For example, Ethernet, Wi-Fi. If it's IPv6, it could even have more addresses here. So that's very simply how it works. The server, in this example, is doing a receive. and the receive is received from. That means that when the receive from returns, we will see here, we do receive from, and what the receive from operation returns is two objects, a data and an address, what is called address here, which is the combination of an IP address and a port number. Those are the source IP address and the source port number. This will be used by the typical server to send a reply. My stupid program doesn't do anything, just prints what has been received, but normally a server would reply, so we know whom to reply to because we have this in this field here. So this is how a simple UDP program can work. Now I have, the program I've shown is IPv4. Now, is there a different UDP for v4 and v6? Hopefully not, because the layering at least should be clean. So IP is different from v4 or v6, but UDP is the same, at least in theory, but in practice, not. Because in practice, if I do everything I've shown here, UDP software, I still need to specify whether the address to whom I'm sending or that I associate with this socket is IPv4 or is IPv6. Because the software needs to know. And IPv4 is 32-bit, IPv6 is 128-bit, so there are different types of objects. You cannot write an IPv6 address into a field that has been reserved for an IPv4 address. So you need to specify which type you do. So when you write a socket program and you do send to, you need before, when you create the socket, in fact, you need to say which type of socket you're using, whether it's a IPv4 or IPv6. So IPv4 is encoded by in the socket using a constant type called AF_INET, that means IPv4, or AF_INET6, it means IPv6. INET means internet, because at the beginning, sockets were thought for lots of things. There were sockets that were not necessarily for TCP/IP, but today we all resume for TCP/IP. So we see this here. We see that when I created this socket, this is IPv4. That's an IPv4 socket. I cannot use it with IPv6 here. If I had decided to use IPv6, that would be fine. Localhost would have worked exactly the same, but I need to choose. How do I know whether I should use an IPv4 or IPv6 socket? Well, that's one of the problems, but the good practice is to not know and write program that will decide dynamically. For example, if I am communicating with a server, I know the name of the server, for example, lca.epfl.ch. I can go to the DNS by calling, the DNS can be called within the socket function. For example, socket get address info, which here I'm using interactively. The beauty of Python is you can write the program or you can write it on the command line. If I go to the DNS by using this function, the DNS server will reply to me what are all the IP addresses that this name has. And I'll see that there is an IPv6 address here, which is this one, and there is an IPv4 address. So here it has both. So my, I would say, professional socket program, not like the toy program I showed, what they will do is they will first do this, and they will analyze, there will be a case. If there is only IPv6, then I communicate with IPv6. If there's only IPv4, I create an IPv4 socket, and then I do my job. If there are both, then I have the choice. Which one would you choose? Well, we don't know. It's embarrassing, right? So most systems will use IPv6. So if you have the choice between new and old, if both work, you use new. Because sooner or later, old will not work anymore. So it's better to use the new. Sometimes, and many systems do that, sometimes it has drawbacks. For example, some systems that are working on IPv4 only, they have what is called interworking mechanisms to allow them to be accessible via IPv6 by essentially adding an intermediate server that will receive your IPv6 query, analyze it, translate it into IPv4, and send it again to the final server. So that will be, and those things are often much lower performance because we do the store and forward in servers at the application layer instead of doing it at the level of routers. So we lose in performance. So sometimes it's not a good idea to choose IPv6 versus IPv4. That's the case for some EPFL servers that are all running on IPv4, most of them. If you access many of them, some of them don't even work on IPv6, like InfoScience, and others, they are working on IPv4, and they have put somewhere interworking mechanisms to still make it available for the very few cases, essentially us and the TCP IP networking class, who so far have been the only ones that insisted on using IPv6. So for those, it works, but with less performance. So it might be a bad choice. So you were right to be embarrassed. That's a hard question. So modern operating systems like Apple system, they will tend to keep detailed quality of service monitoring by when they go to this server, they will keep a record of the round trip time, how much time it took. Because as we will see, TCP keeps a record of the time it takes. And if they find that it's consistently better with IPv4, they will prefer IPv4 if both are available. But that's highly sophisticated, like Apple systems sometimes do. That's for UDP. Now, most of the traffic on the internet is using TCP. And as we have mentioned already, the main difference that TCP adds to UDP is that TCP addresses packet losses. You could say, why do we lose packets? Well, that looks a bit stupid to lose packets. The post office, after all, seldom loses postcards. Right? It may happen, of course, nobody's perfect, but it's extremely rare. So why should we do something special about it? Well, in the internet, it is not. There are transmission errors, which are rare on cables. A sends a packet to B, and then there is an alpha ray somewhere that has corrupted perhaps the processing and decoding of the packet. It's lost. It may happen, but the engineers in communication systems are very smart, and they know the channels, and they code. We know the information capacity formula. The formula says the amount of information you can code without errors, which means, of course, errors will still exist, but you add things like error correcting codes that will correct most errors. So on cable systems, the transmission errors are rare. They're not absolutely impossible, but they're extremely rare. Now on wireless, that's a different story. If you have a static wireless channel, so if you put directional antennas with Wi-Fi and clear line of sight between the two, it will be almost similar to a cable system. But that's not the normal use of Wi-Fi. The normal use of Wi-Fi is, for example, my smartphone in the pocket, and I keep moving. So the channel is changing all the time. The channel is affected by reflections on the walls, and a small movement can change the reflections. So there might be destructive interference that come when I'm here, and they don't come when I'm here, and they come again when I'm there. So the channel is changing all the time. It's very hard, of course, to know what is the information theoretical capacity of such a channel. If I code for one value, perhaps I'm wrong. Plus, you are all around in this room. You're also moving. You have your old systems that are sending electromagnetic signals. If somebody opens a door somewhere, it changes the reflections of the wave. So the environment is constantly changing, even if I'm not moving. So there are losses in wireless systems. It's impossible by nature of the wireless channel to be perfect. So that's one reason. But another reason that's surprising but is very widespread is congestion. Congestion is, for example, assume here I have A and B that are sending over an Ethernet switch to C, and assume the links of the Ethernet switch are all 100 megabits per second. So it's a very cheap switch you bought for less than 30 francs, on the used one you bought on eBay for 5 francs. Modern one would be gigabit per second, but let's assume 100 megabit per second. What happens if A and B are streaming data each at 100 megabit per second to C? They cannot send more because the physical limitation is there, 100 megabit per second. But if both are sending to C for a long period of time, well, the line from the switch to C is also at 100 megabit per second. So something wrong may happen. You cannot push 200 into a line that can support only 100 megabit per second. Fortunately, there is a buffer here. So the way a very, very cheap switch works is it has buffers on input and output. When a frame is received on the input, it analyzes the MAC destination address, goes to so the processor round robin looks one in a row after each of the frames that are at the head of the queue. it reads the first one here, it analyzes the MAC destination address, does the job that a switch, a bridge does. If it is in the table, find an exact match. It finds it for C, it will put it in the queue to C. If the queue is empty, it will start transmitting it. If the queue is not full, then it will be queued. Now, back to our example where A and B are sending at 100 megabits per second each, the queue to C here will fill up because the queue is fed at 200 megabits per second and is written, is delivered at only at half the rate. So there will be a queue buildup at the rate of 100 megabits per second. So after 1 second, there will be 100 megabits in this queue, which is probably much more than the capacity of this buffer. So after a fraction of a second, we'll have a problem. What do switches do when they have a problem? They drop the packets. Some sophisticated switches would send an error signal back to the signal. So would send a, but that's very complicated. It's not done in normal environments. They will simply drop the packets. So that's a very simple example in a simple configuration. But imagine in the internet, when all the packets are coming from different servers to millions of customers on the cellular network of Swisscom, for example, there might be periods of time where there's lots of traffic going to a special part of the network, and the queues in the bridges and in the routers will overflow. That's normal. We'll see that TCP does something to keep this acceptable, but if you do nothing, this is what will happen. So that's congestion losses. If you use a UDP application, you must manage this. So my toy example here, which was working only on local host, was working all the time because on local host, there is no congestion. But if I'm truly sending it over the network, once in a while, if I run my clients, they will send a number of messages and not all will reach the destination. Some of them will be lost. In particular, if I do a loop that tries to send very, very fast at 100 megabits, I will send at the full capacity here. About after some time, when the buffers get full, at least 50% of the packets of the messages I'm sending will be lost. My program does nothing about it, but a normal UDP program should do something about it. For example, if I'm using UDP to do what is called name resolution, when I go to a DNS server to know what is the IP address that corresponds to this, we use UDP. Why? Well, because since I'm sending packet that is a very simple, UDP sends a query and says, what is the IP address of this? You expect a reply. So since you expect a reply, you can know whether your message was lost. You send a query. What can you do to detect whether there was a loss? Well, you can wait for some time. For example, after 6 to 10 seconds. If your reply has not come, then something went wrong. And in most cases, it will be a packet loss. It may also be that the server, the DNS server to whom you're sending this, is congested and doesn't have time to reply because it's so busy that it's put in a queue somewhere. And you don't know which case it will be. But the DNS resolver will care for this. If it does not receive a reply, it will try again. Normally, it will try by going to another server, because typically you have multiple DNS servers. If you have only one, you'll try again to the same server, and will try again and again until this works. This is what you have to do if you use a UDP application. If you use UDP to send data, you must be able to assume that the data might be lost. TCP does it once for all. If you don't want to manage this, you use TCP. How does TCP do it? Well, TCP does what is called management of acknowledgements. The UDP system we saw before was expecting a reply. So a reply was in the nature of the application. But we can imagine to have a reply to the simple fact that the packet has arrived. That's called an acknowledgement. And it's done at the level of TCP, not of the application. So when TCP, here I have a TCP source, A, that sends data to a TCP destination, B. All data is numbered byte per byte. So when your TCP application sends, TCP software sends data, it associates every byte to a number, which is a byte number. It's called a sequence number. So here it has sent a block of 500 bytes that fits in one IP packet. And inside the TCP header, it is written what is the sequence numbers. It is this range of sequence number. The typical notation in TCP means the first number is inclusive, the last one is exclusive. So it means we have 500 bytes here. If this packet is not lost, B will send an ACK as soon as it receives it. So it will send, what is an ACK? Well, an ACK is an empty TCP packet that has nothing, no data. And in the TCP header has some field saying, I have received, and here the ACK means, I have received everything until this number, excluded. Here, again, A continues and sends 3 packets, and 2 of them are lost here. And the third one is received. Then the ACK will be a bit more complicated. The ACK will say, now the ACK needs to signal that I have received everything up to this number. Then there was a gap and there was a block that has been received. So this will be done with this sequence of fields. The ACK field sends everything up to this number was received. And then this block was also received. So implicitly, we discover that there's a block for 8,500 to 9,500 that was lost, which is those 2 packets that were lost here. And what will happen on the destination is when, in a case like this third block of data that has been received cannot be delivered to the destination. This is because TCP is what is called offering in-sequence delivery. Whether it's a good or bad idea, that can be argued, and we will argue that a bit later. But TCP guarantees that the data that you received has been written by the source in exactly the order that you're receiving, which is nice. That means your application does not need to reorder things. If we did not have that, we need to have lots of headers every time to know this is, for example, if I send a big block that does not fit in one packet, I need to remember which part, which block is in. Plus, remember, the internet might misorder packets. So here, TCP refuses that. TCP says, no, if you use me, I'm really the high-end service. When you read from a socket, if you can read, it means it is exactly received in the order it was sent. The side effect is that at this time here, TCP is not able to deliver anything because this has been already delivered. This packet that has been received here is invisible. If the application does a read from the socket buffer, the read will block, or if you insist to make it non-blocking, will say, no, there is nothing to read. Of course, the operating system will keep this in a buffer. So this packet that has been received is, of course, not discarded. That would be stupid. It has traveled the large and hostile world and reached us, so we keep it, but we will not deliver it to the application here. It will be delivered only when this one has been received. So here at time 8, the source has detected the loss somehow, perhaps by receiving this here. Here, this is a clear indication that there is a loss, perhaps. So it resends the block here, and now it's available. If you're curious, you can see that here it sends 1,000 bits, 1,000 bytes, whereas here it had been sent as 2 packets of 500 bytes. That is normal. The job of TCP is to deliver a stream of bytes. Now here it was sent as 4 packets, perhaps because the application was generating them at a given pace. Perhaps it was generating 1 packet. The application was generating a block of 500 bytes every millisecond. So TCP tries to send the data, in principle, as quickly as possible. So it has sent them as soon as they were generated. But the packets are much smaller than the maximum packet size allowed by IP, which is, I don't know in this example, but perhaps close to 1,500 bytes. So when it resends here, there's no reason to send 2 packets. It will fill the packet maximally. So we see here that there's a total decoupling between what was generated by the application that has generated 4 blocks of 500 and what is received by the source, by the destination. The destination has received 1 block of 500, misordered, and then a block of 1,000 that was sent before by the application. Of course, this will be delivered in the correct order by the TCP socket buffer here. So that's the basic principle of how TCP takes care of a retransmission. Question?
Yeah, the packet sent by A number 8. How do we know that there is 1,000 bytes inside?
Well, because in the TCP header, there is this information. This minus that. That's written in the TCP header. It's written how many bytes, and it's written what is the sequence order. In fact, it is written what is the sequence number of the first byte and how many bytes there are. So this is written in, of course, you cannot guess it, so you have to write it explicitly. Now, that was the simple part of the story. In fact, that doesn't work the way we do it, because in the case we saw here, or in the case that we saw here, we say that this has been stored and received. The packet that has been received out of order is stored. It's stored in a buffer. We have seen an example of buffer in switches and routers. A buffer can be full. For example, imagine you're a server. There are millions of clients that are trying to access to you, and then your buffer might quickly become full. So if you do nothing, your buffer at the server might be full, and you might be forced to discard an arriving packet because your server buffer is full. That would be stupid. I mean, the hard thing for a packet is travel all across all the internet and reach you. You don't want to discard something, a messenger that has come from the other end of the world. You say, I'm sorry, I have no place in my queue. So you want to avoid this. And this is why TCP uses a sliding window with a size that's controlled by the destination here. So when what is a sliding window? Sliding window, that is saying that there is a limit on the number of bytes that are in flight. So bytes in flight, that means bytes that have been sent by the source and have not been acknowledged. For example, here, that's a slightly different example than the previous. Here, I'm sending 500 bytes. So at this time, those bytes at time 1, they are not acknowledged. So there are 500 bytes in flight here. When I receive this acknowledgement, there is 0 byte in flight here. Here, when I send this packet and I receive this acknowledgement here, there's a number of bytes, so we're acknowledging this block here. So there is 500 bytes in flight plus 1,000 bytes that are out of order here. And the out of order bytes are considered to still be in flight here. So that means the window size, which in this case is 4,000 bytes, that means that A is allowed to send only 4,000 bytes that are not acknowledged in sequence. Why do we insist on in sequence? Well, because anything that is not in sequence might need to be stored by the destination in its receive buffer. And here, essentially, the destination is signaling to the source that that's the size of my buffer. I have size for 4,000 bytes. So you can send to me any byte from this number to the number this plus 4,000. So I would not be able, for example, here to send 8 packets. I can send 4 packets, I could send 8 packets of 500, but I could not send 9 here. So the sliding window limits the number of bytes that could need to be stored in the receive buffer in order to make sure that the receive buffer never overflows, never overflows. So that's the first part of the story. When we look from A to B, we see that B is sending back the size of the window. We see also that the window may change here. We see, for example, here, there's a number of bytes that have been received. Those bytes in the buffer have been received. They're available, but the application has not consumed them. If you remember the small socket program we saw for UDP, and it's the same for TCP, the data is consumed and the application explicitly does a read statement on the TCP socket, which of course you don't control entirely. The code that runs the application does it at its own speed. If it's very busy or has not yet found the time to consume it, they are stored in the buffer and they must wait until the application reads them here, which is why here I'm sending an acknowledgement with a window that is smaller. And in the meantime, the application wakes up and reads all this buffer. The data that was in the buffer is removed, the buffer is empty, and then we may send, we don't do it systematically, we may send another acknowledgement for the same amount here. We see this is where the window field is changing. So here, B is allowing A to send more bytes than it was before here. We see also another thing is that this works in both directions. Here I said A is the source, B is the destination, but TCP is bidirectional. So A and B are both sources and destination. So A is sending also a window size. That means A is allowing B to send up to 6,000 bytes, which B is doing, here A is sending more than B, which is very typical. For example, when you go to a web server, you send information to the web server, which is your request, get this object, and the web server sends the object. So there is more information in the reverse direction. And there is acknowledgement and sequence number in both directions. Here we see sequence number 8,000, 8,500, which corresponds to acknowledgement 8,500 in the reverse direction. And we see acknowledgement 100, we see acknowledgement 100, yes, which corresponds to the sequence number of the data in the reverse direction. So the values of the sequence number in the two directions are independent. In fact, when a TCP connection starts, we choose a random value for the initial value of the first sequence number here. In addition to, so that's the basic TCP that TCP is doing. So TCP is managing all the losses. If any packet is lost, TCP will replace it by retransmitting it. We didn't discuss how TCP retransmits, but that you can easily imagine. There are timeouts, for example. Also, when you receive information that there is a gap, then you can infer that there was a loss and decide to retransmit things. So it will take care of all possible losses, whatever the root cause, and will also make sure that it's done in a smart way. So for example, if packets is lost, but the destination is busy, there's no space, then there's no point retransmitting it. We have to wait until we receive an acknowledgement with a window that's large enough to allow us to transmit new information. So we see that there is what is called a form of flow control. A TCP source is forced to send data to a TCP destination at a speed which is acceptable to the destination. So the flow of the source to the destination is controlled. You cannot send faster than the destination is accepting because of this sliding window mechanism. In addition to that, TCP does something else, which is called congestion control. It looks very similar, but that's very different, which has nothing to do with transport layer. But again, we found that the internet is made of theories and layers, and then there are NATs, and then there is congestion control of TCP. Remember, we have seen these examples where A and B send through a switch to C. They each send at 100 megabits per second, and after a short transient time, there will be a packet loss of 50%. At least in practice, there might be more if there is inefficiencies in the system here. If that happens, that's very bad for lots of reasons, but there is what we can call congestion collapse. If we do nothing, then we have the internet, which is a combination of routers and switches, but might lose data. Now, this is a simple example where everything is local, but imagine that happens somewhere in California where you're sending data from California to, in Switzerland, when the data is flowing from California to Switzerland, then you've put a lot of data in the transatlantic cable that costs a fortune, and the data gets lost at the other end. So that is not efficient. There's even worse for that, from worse than that. It is called the syndrome of congestion collapse. If you lose data in a complex system, you can have what is called non-monotonicity of the system. The system can become worse and worse. For example, because I lose a lot of data here, those data will be retransmitted. Now, because they are retransmitted, they cause more congestion in the system. There's more congestion, there's even more loss. So the loss might not be 50%, but 80%, which will cause the sources to send even more. So that might make the things catastrophically bad. This has happened in 85, 86. The internet has collapsed under congestion control because everything was, like I said before, congestion control did not exist. Remember, TCP/IP at the beginning was an academic network, not for businesses. Businesses use DECnet or IBM SNA that did congestion control. Congestion control means find a way to signal to A and B that the path between them and C has a capacity that aggregate is 100, not 200. To find a way to slow down A and B when things go wrong. What are things that go wrong? Well, when there are packet losses. So the way this is done in DECnet or IBM SNA is when there are buffers that get full, for example, the packets are marked, they become red. They have a bit somewhere that says packets were congested. And then C returns back to A and B saying, oh, the packets get congested. You should reduce your rate. Here. The internet didn't do that. The internet just did it. That's very much of the way we do it in computer science. We do it small, it works. And then we build it larger, and then we see the problems that come from scalability. At least it has worked a long way. We see with IPv4, we started with 32 bits. Nobody thought that would be too small. Same thing here. TCP the internet does not work with a simple collection of switches and routers. We have congestion that can come everywhere. When congestion collapse occurred in the internet, the IETF decided to add congestion control. Where should we add the congestion control? Well, commercial networks like IBM SNA or DECnet put it in the network layer, but in TCP it was not possible because, as we've seen, the network layer is essentially the postcard problem. So how do I know that there is a problem between A and C? There is a problem between A and C, but perhaps A is talking to another system with which there is no problem. So it's really a property of the path. It's a property of the fact that A and C are communicating. It's not a problem of A, it's not a problem of C, it's a problem of the combination. So the place in the TCP/IP architecture where we know of end-to-end communication, the first place is a transport layer. There's also the application layer, but it would have been worse to put that in the application layer. So the decision was to put it into the transport layer. And in TCP only. In UDP, we don't do it. UDP, the idea is the prototype of UDP is DNS query. You send one message to a server, you expect one reply. If the server doesn't reply, you try something else, you try another server. So there is no flow, there is no long-term flow on which you could change the rate here. UDP applications are not congestion control. TCP applications are. How does it work? Well, in addition to the few examples we've shown before, TCP, we've seen that TCP receives a physical window from the destination that gives the size of the window. That's 4,000 in the example we gave before. In addition to this, TCP keeps a counter called the congestion window, which is given by the source. Window is calculated by the destination and saying to me, the congestion window is computed by the source by an adaptive algorithm, and the actual size of the window used by TCP is the medium of the two. And the principle are when TCP detects a loss, the congestion window is decreased by 50%. When next now we're increasing by 1 minute, it's really outside of the congestion window, it's going on until something like a loss where it's by the and it goes up that is like also this plays a role on the speed of the source only if the window here is larger than the congestion window. Now, depending on which size you have, it may or may not have an effect. So the take-home message is that TCP reacts to losses. When there are losses, TCP reduces the rate. So in the example here, if we would use TCP to send data to C, A and B assume they start at the same time. Of course, we don't send, we also, if we look carefully here, there's also a ramp-up phase, so you don't start immediately at full speed. So the initial value of congestion window is very small, it's 2 packets. So they will not start at 100 megabits per second, they will start at a rate which is a few megabits per second, and then they will increase the rate until they hit the limit of 100 megabits per second in total, and then they will see that there are losses, they will decrease, and they will go up again. It's not extremely efficient. We see that the rate at which A is sending will in fact oscillate between, as soon as if A and B are synchronized, when they reach 50, they will decrease, so they will go down to 25. Then they will increase again until they reach 50 again, and etc. So this is how it will work, which is inefficient if the round trip time is very large. Now, in this example, the round trip time is very small. So the re-increase from 25 to 50 will go very fast. So it will not have a very large impact on performance. If the round trip time is very large, it will have. And so there are additional mechanisms that are called the cubic. So Reno is the example, the congestion algorithm that I described here. The most widespread today is cubic, which essentially does this when the round trip time is small. When the round trip time is very large, it does additional optimizations to avoid spending a lot of time at half the rate. So this is how TCP works. Now, if A, in this situation, if the cable from A to the switch and from B to the switch are the same length, or are both very short, which is probably what happens on an Ethernet switch, A and B will essentially receive the same signals. So if they receive the same signals, they will do approximately the same thing. So A and B will both converge around an average that's a bit below 50 megabits per second, so that we will share the link here at 100 megabits per second fairly between the two. If A, imagine he's on a cable which is extremely long, is 1,000 kilometers, and this one is very short here, then A will have a problem because A will increase, it will receive the thing here, but the rate at which it receives acknowledgement will be much delayed. It will. Also, the increase of TCP says you increase by 1 packet per round trip time. But the round trip time of A is much larger, so the increase of A is much smaller. So A, in a case like this, might perhaps converge around something around 20 megabits per second, when B converges around 80 megabits per second. This is the known unfairness of TCP against large round-trip times. If you have a very large round-trip time, and if you're competing with others that are trying to share the same bottleneck as you, which is this here, then you will receive much less. This is why we push content close to users. If you have lots of people that are trying to get content from California, and those people are in Switzerland, and if the bottleneck is somewhere, the link between the server and the internet in California, the users who are in California will get much, much more speed than us here in Switzerland. So we'll get very bad performance because of this phenomenon here. Worse, if we're accessing over a wireless link, and if there is a loss due to wireless link, what will happen? Assume this link here from A to B is wireless now. That's not an Ethernet switch, but that's a bridge that bridges between wireless and Ethernet. When there is a loss here, TCP doesn't know whether it's a loss due to wireless or due to congestion. There's nothing written in a loss, because a loss is the absence of something. When something is dead, then you can pray or do something, but it's all indirect messages. You cannot know exactly what the dead thing is saying to you. So the losses due to wireless are interpreted as congestion losses by TCP, which reduces the rate. So again, if you're accessing your server in California over Wi-Fi, whenever there is a loss here, your TCP will say, oh, I should reduce because there's congestion. The congestion is perhaps in California somewhere, which will make things even worse. So it's a second motivation for content distribution networks here. Next, in order to do all this zoo of things, TCP needs what is called a connection setup phase. So you cannot, like with UDP, when you send a packet, you send it. You don't warn here. With TCP, you need to do a number of things. You need to agree on the initial sequence numbers, and this is done by sending 2 packets in one direction and 2 packets in the other direction. They can be merged here. So there is 1 round trip and 1 round trip. If you connect to a server, so remember, connection always comes from the client, you send what is called a SYN packet, which is an empty packet, an empty TCP packet that says, I would like to start things now. So that will cause the server to create a socket buffer for you. If the server accepts, if the server is very busy, the acknowledgement of this will not come, and then you have to wait and try again. And then the server will try also to send in the reverse direction, because communication is both ways here. Which means that before sending 1 bit of information, we need at least those 3 things. We need at least a full round trip time here. So if you send 1 bit to California or to New Zealand, you need at least several hundred milliseconds here. TCP sockets otherwise are very similar to UDP socket, except we need, in addition, to do this connect phase. So assume the same program as before. We're trying to send it over TCP. We create the socket as before. The client creates a socket. The server creates a socket, and the server binds to a port number because it needs to be a well-known port number. But before sending, we need to do the connect. What does the connect do? It simply sends these empty packets, and once these empty packets have been properly acknowledged, only then we can send the data. Now we send and not send to, because once this association has been done, we can send only to this specific server. So the server knows who we are, which port number we are, which IP address we have, so we don't need to repeat in every message here. And the server will receive it and will process it. And similarly, when it reads, it doesn't need to know whom you're reading from, because this is done in the association phase. Voila, before oh, no, we will not do a break. Sorry. Oh, sorry. Unless you insist very strongly, you do a demonstration. I'll try to steal the break, if that's okay with you. Okay. If it's not okay, raise your hand. Good, so we continue without break, but we do a little quiz.
ECN.
Pardon me?
What is the ECN? ECN on the EN.
Well, if you don't know it, then you don't choose C. I close the poll in a few seconds. Closing. And the majority says B, which is correct. So here the camera, that's perhaps the surveillance camera in the substation, has lost one packet. And the following two packets, which I'm assuming here those are low resolution camera, one packet is one video frame. But since it's using TCP, the rules of TCP is TCP will deliver in sequence. So frames n+1 and n+2 will not be available to the display here until frame n is actually retransmitted and the loss is repaired. That's how TCP is. We could say it's stupid because video software is able to hide losses. It might be better if you're observing something to have a bit of garble that goes away because there will be new frames that come later, rather than blocking, freezing, which is here what would happen. The video will be frozen until it's repaired. Yeah. But that's what happened if you use TCP. So you have the choice in the internet today. Either you use TCP, and then you don't need to bother about retransmissions, but you will have a behavior like this one. Or if you don't like this behavior, then you need to do UDP, but then you need to do retransmissions or find a way to hide the losses, do flow control and congestion control as well, which is done by TCP. Now, smart grid specific example. Assume I have a PMU that sends data to a PDC every 20 milliseconds. And here I'm showing time flowing horizontally. So you see the transmission and propagation time. What is a better protocol for the PMU? Should you use TCP or UDP? I close the poll. So the majority says TCP, which is probably in most cases not true. And it depends on the propagation and transmission time, but look at one thing that may happen. If a packet that contains a measurement is lost, right? And if the round trip time is not extremely small, it will take TCP some time to detect the loss. I mean, how does TCP detect a loss? Well, there are several mechanisms, but isolated losses are typically detected by acknowledgements that contain gaps. But the standard way of TCP to do that is to, if you have a single gap in the acknowledgement, you can say it might be reordering, so you might not react to it. So you might need several acts to detect there's a loss. But since this is sending only one packet every 20 milliseconds, the loss will be detected perhaps way later. So TCP has a number of mechanisms for detecting losses that are combined all together. Another one is the round trip time. TCP estimates the round trip time because whenever it sends a packet, it remembers at what time it was sent. When this block of data that were in this packet is entirely acknowledged, it also looks how much time it has taken to this. Now, if the round-trip times are not extremely small, this is what might happen. The loss is detected here, and the packet is retransmitted. Now, on the PDC side, the PDC phasor data concentrator that receives all the PMU data, it will see the two packets, M1 and M2, at this time here. So there will be almost 30 milliseconds of delay for receiving M1. Now, the logic of a PMU is that now M1 is completely useless. This is a new measurement. If you do this for historical purpose, you then do TCP, there's no problem. If you do this to control your grid in real time, of course, M1 is useless because M2 has been, if you receive M1 and M2, you care for only M2. Because now time has elapsed, you have new measurements. So here, at least in this example, if the loss detection takes more than 20 milliseconds, then much more than 20 milliseconds, even if the loss detection would take exactly 20 milliseconds, that would force the source to send M1 and M2 at the same time, which takes more time than simply sending M2. So in a case like this, it might be better to simply do nothing, right? Which is okay if you have such a nice periodic application that sends exactly one packet every 20 milliseconds, then you can calculate what happens in your network and make sure there is no congestion. You know exactly the traffic here. So in a case like this, it might be better to do this. Of course, this is also not optimal because if losses happen a lot, you may want to do something about it. But certainly doing TCP might have this problem here. I will skip the section 8. We'll come back to it next week when we talk about security. Question?
Before the last question, how about the arrangement? I mean, if I don't remember wrong, TCP was also providing some encrypted messages, and it's maybe hard to reordering it. Maybe isn't a problem, right?
Yeah, there's no encryption. Okay, encryption is done on top of this. And of course, that's also one of the reasons for using TCP. If you use a simple encryption scheme that is not able to allow reordering, then of course you need to use TCP. But there are encryption mechanisms that are not working with TCP that can work directly on UDP, fortunately. Fortunately, it's possible to encrypt by receiving and decrypting every message independently. Security is an important topic for the smart grid. It's important to know what a MAC address is, what is the MAC layer, what is the difference between a switch and a router. Now you know this. But perhaps more important than all of this is to do everything securely, which is the topic of next week. So we will talk about it next week and come back to this section 8 next week. Right now, for the few minutes that stay, we will conclude with two topics, the application layer and the VPNs. The application layer is the largest part of the internet, but there's a smallest part we discuss in this module here. When you do the phasor measurement unit software and the PDC software, you are doing an application layer. So that's the interesting stuff, but it's system specific, it's application specific. And since we're focusing on the network generic part, we will not say a lot about it. Except that a principle that we have in fact seen many times, the TCP/IP protocol suite is built around what is called the end-to-end principle. The end-to-end principle, which is illustrated here, says that the application and the transport layer should be only in the end systems. That's the principle of packet switching. Seems obvious today, but it's always not so obvious. For example, if you create a new application like BlackBerry, that send messages from one BlackBerry to another. Should we allow a BlackBerry to send a message directly to another BlackBerry, or should we go via servers? When we do Skype audio, should the audio go to a server, or should it go directly from my Skype terminal to your Skype terminal? So the principle of the internet, or the design principle, says you should avoid intermediate things if you can. Why? Well, because it's faster to route packets than to reconstruct messages in a server, write them to disk, and resend them. It's faster and simpler. And since we've built everything around it, congestion control in TCP, for example, it works well. So that's the best to do. If you do your own application layer, you have to do all the things that we do also in terms of congestion, so it's not efficient. Of course, there are cases where we might violate it. For example, if I send a mail to you, I typically don't send it directly from my PC to your smartphone. Although I could. You could have a mail server program in your smartphone, and I could have a mail client program in my PC that opens a TCP connection directly to your smartphone and sends the email. From a resource viewpoint, that would be the most efficient way of using the CPU and the internet. But it would not be very convenient. Why? Well, because my smartphone and my PC are sleeping most of the time. They are not, I mean, this one is sleeping. You cannot send a message to it now. So that's first reason. So if I send a mail from A to B, typically I send it to a mail server, which is the mail server that serves me, for example, EPFL. And then this mail server will send it to the mail server of the destination, who might be here or another one if it's not served by the same mail server. Could send it directly to the destination, but again, because the destination is typically not available, it would not work. So mobility or sleeping is one of the reasons we don't want to do it. For mails, there's another reason, which is security. When I send a mail server to you, in fact, what the mail server will do is analyze it to see if it's spam. And in fact, more than 80, I believe, not even 90, more than 90% of the server received by email, by the email servers of EPFL, is destroyed. So most of it is garbage, which is destroyed. So it's better to do that on servers than on your system here. Same thing, we don't want to have server ports open on our system. We prefer to leave it to data centers that invest a lot of resources into analyzing the garbage that is polluting the internet here. Sometimes if you go, for example, to an electric company like Romande Energie, and you sit there, you will see that you're not able to access the internet directly. Instead, they have put in place what is called an HTTP proxy, where when you go to the internet, you first go to an intermediate system that will screen whether what you're doing is okay and perhaps forbid you to go to eBay or Amazon to buy, or Migros, Le Shop to buy your food, because you're not supposed to do it on the work, and also to protect their computer infrastructure from access to sites that might be polluting. So that's another example for security or access control, where instead of going directly to a web server, I go to an intermediate system that repeats it. That's of course at the cost of performance, but it has a value in terms of security and isolation. Here's an example from the Smart Grid book that I give as a reference on Moodle of the book, of the course, where I have a number of devices that are the smart meters. So smart meters are implementing TCP/IP. You can talk to them, you can read what they have, and they can receive information to be displayed to the users. Now, if I have all those meters that are sending information to a system that gets all the data from the meters, what is typically done is to have what is called a meter concentrator at the end of the power line communication systems that connects to the utility, to the electrical company, via a communication network that might be the standard internet or a VPN. If we apply the design principle of the internet, what should the meter concentrator be? Should it be a switch, a router, etc.? I close the poll in a few seconds. Closing. And the majority says B, which is probably right. I mean, the switch would assume that this is a very small network, so might also be acceptable, but probably most of the times it should be a router, which is probably not the case in most cases for probably bad reasons. So very often smart grid networks introduce more complexity than is strictly necessary. If everything is, for example, properly secured here, you have a VPN there, that simply should be a router here. But there might be bad reasons that make this impossible. And one bad reason is very often that you want to decouple the software that's on the meter from the software that's here. Perhaps the software that's on the meter is able to speak only is deployed by Siemens, for example, and this is deployed by ABB or by another company, and they are not compatible. So if they are not compatible, then you put an application layer gateway that will be able to solve the problem. It's simpler to solve the compatibility problem in one computer here than in every meter, or in the application program here, because it's sometimes complicated to change a company's logic here. But that's often a bad reason, but that may happen. You also find even worse reasons. You have sometimes smart grid networks, like I mentioned before, that don't use TCP/IP or use it in a strange way, such that you don't want to mess with it. So that's why sometimes you put also something else here. Voilà, we will conclude this session and this first part of this module with a small discussion of virtual private networks. That's a topic that is visible to all of us. When we connect to EPFL from home, for example, and we want to go to IS Academia for a few things, we might need to be in a virtual private network. So what is a virtual private network? Well, there are different use cases. Here is a simple use case that's very typical of a smart grid environment. Here you have a substation. Here you have another one, and you want to interconnect them. You want to interconnect them. If you have your own private network, that's fine. But more and more, you want to use public networks because they are cheaper, at least for non-mission critical duties. And here you will tend to have your own network where you use private addresses. You use private addresses for lots of reasons. First, because it costs nothing. You don't need to ask anybody for an address. And second, it's truly private in the sense you're sure no traffic from the outside will be able to connect to those machines here because it's a non-routable tool. You cannot reach destinations here. But you have a problem. If I want to connect via the public ISP, then of course you cannot. So you can put NAT, we've seen that, but you have in addition a problem is that you want to protect your traffic on the path here. Protecting it means typically encrypting it. So you place them inside a TLS connection. So TLS connection is something from the section we've skipped, but we will see next week. A TLS connection is a security association you build on top of TCP. So you establish a TCP connection between A and B, which is strange. Those are like routers, but now you open a TCP connection between the two. And in addition to this TCP connection, you encrypt everything. Right. That is called TLS. So you normally do TLS when you go to your bank. From client to server, we use TLS to go to a bank, as we will discuss next week. You can also do it between two boxes here that are called VPN boxes. And if we look at the packets that flow here, for example, when X sends a packet to Y, X is perhaps a PMU, Y is perhaps a PDC. When it sends the packet to Y here, if we use VPN in this way here, B will send the packet will put the packet of X inside a TLS connection, will encrypt it and put it inside a TCP packet. So since it's encrypted, I cannot read it. It's like random bits for me. If I am able to decrypt it because I know the secret key used by B, for example, I would read an IP packet with an IP header from X to Y, and perhaps it has a TCP header, if this is TCP, perhaps a UDP header, and the application data. All of this encrypted is put here. Then the encryption requires some additional header and trailer that contains fields that are necessary to know how to decrypt. Of course, the secret key is not contained. The secret key is known by A only. So this is the blue part is put inside a TCP packet. The TCP packet has a TCP header that says destination port 443. That's a standard port used for that kind of things at A, and source port, the source port used by B here, which might also be another number. So if I do a Wireshark of this packet here, I will see the TCP header. I will also see a TLS header, but I will not see the data. I will not see what is contained. I don't know whether this guy is doing e-banking to a bank or is sending an IP packet to Y here. And then there is an IP header that says destination 111 and source IP 222 here. This is called encapsulation or tunneling. Those are two synonyms. We call it a tunnel because it is as if we had dug a tunnel through the internet from A to B. Well, it's called encapsulation because we put the IP packet inside TLS, inside TCP, inside IP. So this is how VPN typically works. It can also be used instead of doing interconnection of two sites. It can be done of interconnection of a standalone machine. And this is what you and I do when we access the VPN of EPFL and we are not at EPFL. So we do the same thing inside our PC. We establish a TLS connection to what is called a VPN server or VPN router of EPFL here. And inside this connection, we put the encrypted packets here. And the VPN software will give me the impression that I am sitting at EPFL. In fact, it will create what is called a logical interface. It's logical because it's not a physical interface, but from the operating system, when we do ifconfig, it will appear as if it would be a physical interface. Here I've done an IP config that's over Windows, and I see here my IP address at home, network mask, a default gateway, and I see another interface, which has called Ethernet 2. That's the way this Windows system called it, with IP address, an IP address of EPFL, and a subnet mask, which is 32 bits, which means essentially I have a physical link, which is my tunnel from A to the router. It is as if I would be connected by a long, long cable from my computer to the router. And it's a network, which only me on it, from the router viewpoint. This is why the mask is 32 bits here. I am the only one to be on link with the router on this system here. So now I have two interfaces, and hopefully my computer is smart enough to know that when I send something to the printer, I should send it via this interface. When I go to a web server of EPFL, I should go via this interface here. So if we do a Wireshark here, somewhere in the internet between me and EPFL, like before, I will simply see, I will only be able to know that I am communicating with this router, but I will not see the packets. I will not see the source IP address and the IP destination address. I will not be able to know that A, for example, is communicating with B. This is all encrypted and invisible here. What I explained is tunneling in TCP. This is one of the two variants. There are zillions of variants that are used. The most frequent variance is IP in UDP instead of TCP for one reason, because when I open a tunnel between me and the VPN router, all my so in this example, it's even more illustrative. If A and B open a TCP tunnel here, rather than UDP, TCP will do lots of nice things like retransmit the packets, but you will also do one thing called congestion control, which is good or bad, depending on the viewpoint. but it means that if there is congestion on the public operator, this line here will reduce its rate to make space to others. Since TCP is sharing more or less fairly to all users who have the same round trip time, here, all my traffic going from A to B is counted like one user. Assume there is a bottleneck link here. There is a link that at 1 megabit that has only 1 megabit per second of capacity. The link is perhaps at 1 gigabit per second, but there might be thousands of applications that are running, and it leaves only 1 megabit per second available for all traffic that goes from here to here. And assume there are other flows that are going here. If there are 1,000 other TCP connections of people that are not using VPN, but are just going on the same link, then my tunnel is just one of them. So I will have 0.01% or 0.1% of the capacity for the entire traffic here, like each of the 1,000 other individual users. That's why TCP tunnels sometimes have very bad performance. If there's congestion somewhere, they reduce, like they adapt like everyone. Plus, if you're using TCP from X to Y, you will also adapt. You will also reduce your rate. So you will reduce twice, which means you will be at an unfair situation compared to others. So because of that, we often use UDP or IPsec, which is similar to UDP, mechanisms that do not do congestion control. Voila. And that's the end of this module. So I've tried in a crash course to teach you all you need to know about TCP/IP in 2 weeks. Because you will be exposed to it when you write software for a PMU. You will have to decide whether you do a UDP socket or a TCP socket. Perhaps you will have a network engineer that will do some of the work for you, but be careful of network engineers. Did not all have network courses. So sometimes they just know how to make it work, but they just follow what ChatGPT says, which is not always the correct thing. So it's better to know the design principles. And in this fascinating world, the beauty is that there's a large number of very easy tools. I've illustrated some of them in the slides. You've had the opportunity to use them in Lab 1 also, that allow to explore things very easily. Voilà, thank you very much.